Okay, we're back. Okay, so let's pick up where we left off. Okay, can everybody online see the screen okay? Excellent, thank you, Kendall. Okay, so look about right, about where we left off. Okay, so we're talking about elements. We wanted to, we kind of like pulled all the different elements together. We kind of got some ideas about how some of this work. Now, what we want to do is we want to start kind of moving forward with this with this idea, and we want to start moving toward bonding, right? So we want to start putting molecules together. As soon as we start putting molecules together, we can start making cool stuff like proteins and DNA and things like that, which is going to be the topic of the next chapter. So let's go ahead and kind of round this idea out a little bit, and then take a look at it, right? So basically what we said was that we have 90-ish or so naturally occurring isotopes for the most part. And those are just the ones we find in nature, right? So if you're wondering, like all these ones up here on the periodic table that are kind of like clear, or the ones that are kind of down, especially the ones that are clear, not so much these. This is uranium, which is up to 92, so that one you can find in nature. So if they're black, they're typically found in nature, so you can stumble on them within the bounds of their natural abundance, right? So the clear ones are, I don't want to say fake, but these ones, some of these only exist in like our imagination. And by that I mean they actually exist. We've actually documented them, so they're not like stories. So they actually documented them, but these are things that like that we've only created when we slam nuclei together, like in our super collider and CERN, and they last for maybe milliseconds, right? So it's not really useful for us. If you're a physicist or a particle physicist, I mean, that's kind of like your geek zone. And for you, that's kind of already immediately interesting. But for the rest of us who actually want to put this to work and use it for something useful, it's absolutely meaningless. Right? These are useless for us, these clear ones, because it doesn't do us any good if it's only made in a super collider and it only lasts for a few milliseconds, right? That's not helpful for us, because obviously we last a little longer than a few milliseconds, and we need our atoms that we're made of to last a little bit longer than that. Okay, so that's not really useful, although it is interesting when it comes to our particle physics sort of thing. So of all the 90 naturally occurring isotopes, the ones that we can stumble on in nature, in biology, we would naturally probably ask the question, it's like, okay, this is great. We only got 90 of them or so. So let's go ahead and use all these, right, to build them all a biological organism. Well, as it turns out, we don't actually need all 90 of the naturally occurring, because there's only so many atoms actually in living things. So for instance, if you were to take a living organism and basically break it all down into just like atoms, then what you would see is basically this list of 12 atoms. That's what all living organisms are made out of. That's it. So of the 92-ish or so naturally occurring elements, we only make use of 12 of them. By the way, there's a discrepancy, yes, because uranium right here, you can't see because it's hidden behind the screen, is 92. And the question oftentimes students say, wait a minute, you said there's 90 naturally occurring elements and we see 92 up here. So what happened to the other two? Well, the other two kind of have some little weirdnesses associated with them. Like for instance, this guy right here, which is slightly different. So this is just purely what we can find easily in nature. Some of the original 92 we can find in nature, although it's not very easy to find them. That's why this is kind of like a parenthetical at this particular point, because it's not really something we see a lot in nature. And that's something that we see from time to time, which actually is interesting. We see it in the solar system. There's like some, like we have the interesting thing is that when we take a look at the Earth itself, the Earth has, of all the atoms in it, a natural kind of a ratio of all of these naturally occurring elements in the Earth itself. That's not the same as it is on other places of the universe, right? So other areas of the universe will have different ratios and will have different elements associated with them. This is one of the reasons why geologically sometimes we can figure out whether or not there's been a meteor that's collided with the Earth, because all of a sudden we'll see this like spike in a very rare element on Earth in a particular area. And then we say, so, well, this is something we see very commonly or in high proportion, say, for instance, on an asteroid or a meteor or something like that. But we don't see it, you know, on Earth. So that suggests then that that's kind of forensic evidence, if you will, that at some point that there is some sort of a meteor that hit the Earth and left all of its rare elements in that particular area. And that's kind of, so those are always fun games to play, right? Especially when you go to Arizona and you see the meteor crater. And the idea is like, well, if something from outer space hit this, then you would expect the elemental ratios to be a little bit different. Okay, that's all here. That's just all fun, right? But let's get down to business. So our business is basically building a biological organism. So the question is, what do we need in order to build that? Well, we know we need these 12, but however, not only that, but we also need basically 4 of these. So of all these 12, more than 96% of these are made up by 4 of these atoms: carbon, hydrogen, oxygen, nitrogen, CHON. Okay, so this is the overwhelming lion's share of what's actually in your molecules. So when you break down your molecules, you are primarily carbon, hydrogen, oxygen, and nitrogen. Now, what about the rest of these? Well, the rest of these are basically what we refer to as trace elements. That's to say that there's not a whole lot of them in there. But one of the things I always like to do is, with this particular slide, I always like to sort of break students down. I like to break students down and kind of get, we in the West have a very Texas mentality, right? The idea is like bigger, better. If it's big, it's good, right? So we kind of have this sort of one-to-one thinking sometimes that all the stuff that's like really big, or if you have a lot of it, it must mean it's a good thing. And it's kind of a sickness of our democracy, right? Because the idea is the more people you have from a party, then the more in control they are. So more is good, right? So there's kind of like a lot of reinforcement in society for more is good, but nothing could be further from the truth when it actually comes to biology. And biology really is the story of how the tail wags the dog, right? So primarily you have the dog, CHON, right, 96%. But the dog can't really do a whole lot unless it has a couple of major things. Let me take a look and just try to pull this out, what I mean by this. And I want to use sodium. Now, sodium, if you take a look at all the atoms in your body, is a tiny fraction of the overall atoms that make up your body. However, if you don't have sodium in your body, you'll be dead. So it is critical. It's not a lot, but what you need is you need it, right? So it's a very critical sort of a thing. Why? Well, you'll learn this when you get into physiology. Sodium is actually the ion that is necessary in order to send a nervous impulse. So right now, your neurons are firing, connecting each other, trying to learn new pathways to sort of understand new information. And sodium is behind all of that. Okay. So if you don't have sodium, then literally you would have absolutely no nervous impulse. You have no capacity to think, you would have nothing. Okay. Let's get actually worse, right? Calcium, we usually appreciate calcium because we think, oh, well, you need calcium to grow and all that sort of stuff. And that's true, but calcium is also a tiny fraction of your overall body mass. However, again, this is another one where if you don't have calcium in your body, you're going to be dead. Why? Because calcium, among other things, isn't just like a component of your bone, right? We always think about calcium, drink your calcium, like drink milk or whatever, so your bones will grow strong, right? We always hear about that one from like when you're little and that sort of stuff. But actually more importantly is calcium is actually the major signal in your physiology for muscle contraction. So if you don't have calcium, you don't contract your muscles. Which is fine, right? You're probably thinking, well, that's okay. I mean, I can just go through life as a vegetable. I mean, I'll still be around and, you know, I may not be able to move a lot, but I'm okay with that, right? No, not right. Because guess what else is a muscle in your body? Not just your skeletal muscles, not just the ones moving your arms and legs. Your heart is also a muscle that also requires calcium. So if you don't have any calcium, you don't fundamentally have a heartbeat, which means you're dead. Which is the reason why calcium deficiency is no joke. Okay. How about another one? Iron. Anybody do without iron? No. What does iron do in your body? So iron is actually one of the major components of blood. So your red blood cells are full of a protein called hemoglobin. They're complexed with iron. And the iron is actually how your hemoglobin binds to oxygen. So the oxygen in your blood is actually bound to iron. And that's how you deliver oxygen throughout your blood. Now, what happens if you don't have any oxygen in your blood? You're dead, right? Matter of fact, there's an entire disorder, right? Iron deficiency anemia associated with this. So basically anemia is your lack of ability to deliver oxygen, which is a lethal situation. Okay. So notice there's not much, right? We're not talking about a ton of it. We're talking about a little bit of it, but they're absolutely critical. So they're trace, but critical. Think of it in terms of like culinary training, right? I mean, if you're anything like me, you've got the palate of a cow's backside. So, you know, you can pretty much eat anything and be happy with it. But if you're like a culinarily trained individual, I don't know if you've ever run into somebody who's like has culinary training. They are trained like like my eating habits would probably turn most culinary people sick, right? Because they're like, seriously, I mean, you don't really need that salt. How are you gonna taste it? It tastes good to me, so I don't really care. Right. So what happens when you like are cooking a dish, like you're culinarily trained? You don't see a dish like just sort of tossing it all together so the kids can eat it, right? Or putting salt on it so you can, you know, that's not the way you look at it, right? You look at like a dish, like a piece of art, where everything and every flavor is in balance with each other. So when you cook, say, for instance, that pasta, you're not just slamming a bunch of tomato sauce in there and just hoping it sticks, right? I mean, you're like really working to balance those flavors. And then oftentimes your spices, garlic, for instance, which I love, you know, you don't just put the entire clove in there, do you? A little bit will go a long way. And not only that, but you only put just the right amount because the idea is for it to have balance with all the rest of the flavors, not to overwhelm anything, right? Now, if you're like me, who loves garlic, then overwhelm it all you want, right? Because I'm happy with that. I just eat the garlic by itself like an apple, right? So I'm happy with that. But if you're like a culinary person, you're trying to balance all those flavors. So even though the garlic is a tiny proportion of the overall palette of flavors in the dish itself, it is also a very critical component, right? Because without the garlic, it loses the fundamental effect of the overall dish. And that's kind of the way some of these ions are. Okay, now that's all well and good. So we got our atoms down, we got our elements down. Now we know which ones are at play, right? We know that Chan is the heavy lifter. That's most of what we are, but then there's a whole stable of there's a whole stable of associations. I'm reading this at the same time as I'm talking. There's a whole stable full of these trace elements that have a lot of important physiological functions associated with them. So the question is, how do we start putting these things together in meaningful ways that will give us biological activity? Okay, that's what we're after. And that's going to basically come down to how do we actually bond them together. Now, remember, when you take a look at a bond is essentially an arrangement between two atoms about their electrons, not just any electron, their valence electrons, such that they satisfy each other's octet rule. Remember the octet rule? What was the octet rule? yeah, they do whatever they can, right, to fill out their valence shell. In this case, they're forming chemical bonds. And so as a pair or as a group, and within that relationship, they're able to satisfy each other's octet rule. That's an important thing when you're talking about bonding. Is the reason why they're doing this is because they're trying to become perfect. They realize they're not perfect on their own, but if they can complement with another bonding partner, then they can cover their bonding partner's imperfections and make them perfect, and their partner can cover their imperfections and make them perfect. And so within the context of the relationship, then they achieve their perfection. We've kind of already talked a little bit about it, right? So we kind of talked a little bit about how chlorine and sodium behave and how close they are to each other and the strength of their personalities. Well, that's actually one of the first of three major types of chemical bonds. It's the ionic bond, actually. So this is a situation where you have the gain or the loss. And so, for instance, the formation of sodium ion is example, so chloride ion. Right, this is basically where there's such a strong relationship between them that that's essentially it looks like a gain or a loss of an electron. So it's a total absolute transfer of the electron. However, this is not to be understood as the same thing as like a redox reaction, right? Remember we talked about a redox reaction where you had a gain or a loss of an electron. That gain or loss of electron is generally speaking mostly associated with energy transfer, and it doesn't change the identity of the molecule, right? So like, for instance, the difference between this and a redox reaction is in a redox reaction, I don't become ionic, right? So the fact that sodium forms a positive ion and chlorine forms a negative ion means that there has been an actual permanent disposition of the electron, right? That's not what's happening in the redox. I'm not like if me and Connor are both two partners in a redox reaction, then when I pass on electrons to him, I don't change my electronic identity. I still am who I am. I'm neutral. I have the same number of electrons and protons and so forth. And so does he. He just has kind of this new bolus of electrons that he just sort of passes on. So you can almost imagine that the electrons that are passing through a redox reaction are separate from the atom's complement of electrons that it has as part of its identity. Does that make sense? So it's not the same thing. So here's kind of what you see, right? So in our ionic bond, you can see you've got a sodium who takes this electron, will give it off to chlorine. So that sodium in its happy place will exist as a sodium ion. And that's the way it wants to exist. So if you see a sodium ion, it's happy, right? Because it's achieved its octet rule. The chlorine, on the other hand, will have gained that electron, so its happy place is as the chloride ion. So it's picked up an electron, so it has a -1 charge. Now, when you take a look at this one, this is just basically table salt. Then we all kind of know table salt is a nice little crystal, right? So we shake it out. It's little crystals of salt. What those little crystals are actually this guy right here. So this is an actual salt crystal. And because they're ionic, that is to say positive or negatively charged, then what happens is they stack in such a way that the charges will align with each other. What does that mean? That means the positives will surround themselves with negatives, right? Because that's an attractive sort of a thing. Positive is a repulsive sort of a thing. So you don't want to do that. That creates a lot of tension and causes you to want to fly apart from each other. So you can see here how a sodium will surround itself with the negative charges of chlorines. This chlorine surrounds itself with the positive charge of the sodium. So what you're doing is you're stacking these things, basically positive to negative, in kind of an orderly, in this case, a kind of a cubical square crystal. Now, different crystals have different shapes to them based on their ionic nature. So if you ever actually look at the crystallization, like up close, and study the crystallization of different types of salts, you'll see that they have different patterns of crystallization that are associated specifically to their ionic characteristics. Okay. So different salt crystals will have different types of crystallization. But that's our favorite, right? That's our beloved sodium chloride. Okay. Now, what about covalent bonds? Well, here's what I want to do. Because we've already kind of started talking a little bit about it, what I want to do is I want to maybe move that here, and I'm going to insert a slide. I want to put them all in one place. And I want to sort of pull everything together, but sort of wrap it around the primary motivation for bonding. I mean, we've already talked about octet rule, and that's a thing, certainly, right? But now what I want to do is I want to talk and put them all on the list and sort of couch them within the context of one particular physical property that sort of draws it all together. So we already talked about the first one, the ionic bond, which we can define as two atoms that have an extreme difference in electronegativity so that electrons are transferred between them. And this typically occurs between a metal and a non-metal. Okay. Couple of things we need to clean up on. First of all, I want to start with the metal non-metal thing because that's part of our periodic table understanding. But then there's a big word in here that I tossed in there, right? That I need to define. And that's the one I want to use to pull everything together. First of all, a metal with the non-metal. So where are the metals? Yeah, so we got a bunch of metals over here, right? So the alkaline metals, the alkaline earth metals. So those are metals. Highly reactive, right? Very, very reactive. Why? Because they're really, really close to perfect, right? So they're super close. That's why they're so reactive. Of course, then you have a bunch of transition metals in here. Typically, we don't do a whole lot with that in biology, chemistry. You hang out here for a long time. And then, of course, you have your non-metals over there. And then there's a little zigzag line that kind of goes right in between, you know, aluminum and arsenic and lead and polonium right there that are kind of like, that's kind of like a transition zone from the metals to the non-metals. So for instance, oxygen, sulfur, bromines, those are all non-metals, okay? And so typically an ionic bond is occurring between some type of a metal and some type of a non-metal. Okay? That's the reason why we did sodium with chlorine. What is sodium? It's a metal, it's a soft metal, very reactive metal. You have to handle it with gloves or it'll tear you apart. And then of course, what's chlorine? It's a green gas. So it's a non-metal. So any one of these actually, with any one of those non-metals will actually work. And that'll be an ionic bond, okay? So there's a lot of things. And generally speaking, usually when you're looking at ionic bonds, you kind of usually will use kind of like the idea of like, you'll use the term salt as sort of a generic descriptor of the ionic situation of a metal with a non-metal. So when I say salts, plural, not table salt itself, but salts, plural, that's what I'm usually referring to is the entire spectrum of possibilities. So calcium chloride, that's a salt, right? Sodium chloride, that's a salt. Potassium bromide, that's a salt. So any kind of a metal, non-metal combination is usually what I refer to when I'm referring to it as salts, a type of salt, okay? Okay, but let's go ahead and define something first of all, and that's electronegativity. So what exactly is electronegativity? Well, electronegativity is an important physical property of elements. As a matter of fact, there's a series of actual physical properties, which is kind of cool, right? Because in chemistry, generally you'll hit electronegativity in a period in chemistry where they start looking at the periodicity of the periodic table. And what does this mean? So what this means is the cool thing about the periodic table, the reason why the periodic table is so awesome is because when we first developed the periodic table, what we did was we essentially arranged these atoms by atomic number, right? Which makes sense. 1 proton, 2 protons, 3 protons, 4 protons, right? That makes a lot of sense. And so as it turns out, though, that just by ordering the periodic table by atomic number, it turns out that we're able to actually predict chemical behavior. And this is true not just for electronegativity, but it's also true for a lot of other physical intrinsic properties of the atoms themselves. So when you actually get really into chemistry, you start learning about the chemical traits and behaviors of these elements, you'll realize that, wait a minute, all I did was just order you by atomic number, but now all of a sudden this whole document can become a predictive tool for all these crazy traits. And it's just like, it just like was luck, right? Because I mean, Mendeleev wasn't thinking about like, I think I want to organize this so that it pulls all these chemical traits together. He didn't realize how many chemical traits there were of all these elements. It just so happens that it was just luck, right? I mean, think about it. All you do is organize this by atomic number, but now we have a periodic table that also organizes our valence electrons, doesn't it? Right? Group 1, group 2, 3, 4, 5. And by the way, that's also predictive for the ions as well, right? Because you have group 7 is a -1 ion, -2, -3, right? So you can predict the ion states as well. And there's an entire laundry list of chemical properties and traits that we can predict just from this periodic table. That's what the whole periodicity part is of it. And actually, the more of those layers you kind of go over, I mean, it's like your jaw drops. And you're just like, this is like absolutely amazing that we were able to just do something so simple, just order it by atomic number, and it basically predicts all of this information. And that's because the alternative, by the way, which is a reasonable alternative, is this is probably what we're thinking. Okay, we're going to order it by atomic number first, but we're probably going to have to reorder this like by electronegativity because it can't possibly be the same. So we're probably going to have to rearrange everything and say like, well, if we're going to arrange you in terms of high to low electronegativity, then we're going to have to scramble everything all up and it's going to be a different looking thing, right? And you can imagine you could potentially do that for every single chemical trait. But as it turns out, everything actually falls exactly into line, which is like, if you think about it and just allow yourself to step back and take a look at it, it's kind of a little jaw dropping, actually, how simple it was to just order it, but how also important it is for the atomic number. So when we say the atomic number is your atomic ID, all of that comes along with your atomic ID, right? So that's the cool thing. So this is one of those periodic things. So what exactly is it? That's nice, but what is it? What is it? So this is basically the official definition, right? The affinity that an atom has for electrons. Basically, this is electron suckiness. That's my not so official technical way of looking at it, right? I used to say electron magnetism, but that gets confusing because magnetism is actually a physics thing. It's actually a physics force, and it can be confusing. It's not the same thing. And magnetism does interact with electricity and electrons, so that gets confusing. That's the reason why I stick with suckiness, is because there is no biological equivalent for suckiness. It's basically an atom's ability to suck electrons toward itself. And some atoms have a very strong sucking effect on electrons, and some do not, right? So how does it change? Well, it's very easy. You can tell very easily, very quickly, what the electronegativity is of an atom. Why? Because electronegativity, here's my periodic table, increases going up and to the right. So what's the most electronegative element that we have on the periodic table? Not helium. The nobles don't count, right? Because they've checked out. They're perfect. Who? Fluorine, right? Because it's the most up and over to the right. So that has the highest electronegativity. Who has the lowest? Huh? Oh, Kenna, the noble gases don't count, sorry. Because they've already checked out. They're already perfect, so they're out. So this one, right, whatever FR is, because it's the furthest over and down, so that's francium, right? And so the nice thing is you can basically predict electronegativity differences depending on where you are on the periodic table. It's very simple. It's like, well, how far up and over are you relative to each other? And generally speaking, you're usually looking at relative differences between two atoms, right? Because if you take a look at a bond, you have two different partners in it, and you're looking at their relative electronegativity. So let's take a look at an example here. A covalent bond example. So here what we have are a series of non-polar covalent bonds. It's one type of a covalent bond. So let's take a look at it. So hydrogen, which has how many valence electrons? One, right? We'll see another hydrogen and they're like, hey, this is nifty. We need two. You got one, I got one. Let's go ahead and share it. Boom. You just made a bond, just like that, just that easy. And of course, that basically gives you this right here. So the line between two atoms basically represents a pair, in this case, of shared electrons. Now, here's the thing. You're going to share them, yes? But the electronegativity of this hydrogen here versus this hydrogen here, is it larger, smaller, or equal to? What? Equal. Why? Yeah, they're the same thing. It's, yeah, that's not a trick question. It's the same, right? So that means that if they're the same, they're non-polar. That is to say they have the same amount of suck on them. They're sucking these electrons equally. Let's take a look at another one. Oxygen, which has how many valence electrons on it? 6, right? 1, 2, 3, 4, 5, and 6. And then 1, 2, 3, 4, 5, and 6. So here now oxygen sees another oxygen. They're like, hey, wait a minute. I got one. You got one. Let's share it. Boom. Got it. Okay, there's a bond. And they're like, you know what? I got another one. Do you? Like, yeah, I got another one. You want to share another bond? Sure. Why not? There you go. Now what you just made is a double bond, which is stronger than a single bond. And you see these a lot in biology. Matter of fact, the structure of carbon dioxide is carbon doubly bound to two oxygens. Now, there is one atom that can form 3 bonds. That's a triple bond. That's very rare. Nitrogen is the only one that can form that. So here you can see there's one bond there. There's another bond there. There's another bond there. Doing the same basic process. Hey, you got a pair? Yeah, let's go ahead and do it. You got one? Yeah, let's go ahead and do it. You got another one? Yeah. Okay, let's go ahead and form a third one. Boom, there it is. You got 3 bonds in between the two of them. Generally speaking, nitrogen is usually involved in this. This is what nitrogen, elemental nitrogen actually looks like. This is a major component of the atmosphere. Some people don't realize that our atmosphere is actually mostly made of elemental nitrogen. That's what it is. This, by the way, is also the one that gives us problems when you have the bends, right? So if you come up from a pressurized area from diving too quickly, you don't allow the nitrogen gas a chance to dissolve. So it comes up as bubbles. It's like basically you're physiologically making yourself a 2-liter bottle and you're opening the top. So all those bubbles come out in your blood and they get stuck in your joints and they cause all sorts of physiological damage. And that's basically the bends. Any other molecule that has 3 of these bonds in them typically are associated with nitrogen. For instance, I think sometimes you see this one here. It came up in class last week. What is that? I don't know what that is. I used to, back in organic chemistry, I used to know that one. It's very rare, but it's some sort of an amide. But this is rare. So you see lots of singles, some doubles. Very rarely do you see a triple. Okay, but these are all non-polar covalent bonds. Why? Their electronegativities are the same, right? Oxygen, same stuff, same, right? Nitrogen, same stuff. So it's the same electronegativity. Okay, so that's basically your covalent bond. So let's kind of properly define this one. This is basically where two atoms share electrons between each other. Now, a couple of buzzwords. First of all, in ionic bonds, the buzzword is the transfer of the electrons. In covalent bonding, the buzzword is the sharing of electrons. And we've seen one of the two types. So you have nonpolar covalent. This is basically where two atoms share electrons equally. And then there is polar covalent. This is where two atoms share electrons unequally. So how would this work? Let's take a look at a polar bond. Let's say we have hydrogen with one bound to an oxygen. Now the oxygen obviously has to be bound to something else, right? Because it has another one. So we're not interested in that. We're just looking at this one. Is this a polar bond? How about the electronegativities? Is there a disparity in electronegativities here? Who's the stronger? So the electronegativity of oxygen is greater than the electronegativity of hydrogen. So what does that mean then? If your electronegativity is higher? Well, what that means is, remember, you have a stronger sucking effect on your electrons. So what that means is that oxygen is going to suck the electron cloud toward itself. That's what that means. That's what the electronegativity does for you. Remember, when these two atoms come together to share electrons, they're not just sharing their electrons, right? But they're also, there are those orbitals, those like little pea-shaped, peanut-shaped cloud, orbitals in the cloud. That was for like one atom, right? But if you have two atoms coming together, they're bringing their little orbital rosette into close proximity to another atom's orbital rosette. And all those electrons together will form the overall cloud of the molecule, and they'll kind of have to rearrange themselves. Okay. And so that's going to be part of the process. And so that's what's in your overall molecular cloud. Now, what this is saying is that when you have a high electronegativity, then you're going to have a sucking effect on those electrons. You're going to like bring them to you more so than your partner. So what does this give us then? So what this gives us is something nifty. Let's take a look at this one. What is that? Yep, that's water. Who has the higher electronegativity? Oxygen, right? So when you have a water molecule, what's going to happen is the oxygen, because of its higher electronegativity, is going to be sucking the electron cloud toward itself. And so those electrons are going to be spending more of their existence around oxygen and not so much around hydrogen. That basically means is, with the accumulation of electrons on this end, it's going to make water look kind of negative-ish on this side for the oxygen. Now, relative to the oxygen, the hydrogens are going to look a little on the positive-ish side. What have I created? What I've created is a polar molecule. What does that mean? It means it has two poles, a positive and a negative pole. In chemistry, we refer to this as a dipole. And water is what we refer to as a permanent dipole. That means that's the way it exists. It exists something like this. I've always got a negative side, right? There's my negative, and I've always got a positive. And that's the way I am. That's the way water is. It's always got a negative end, So it's got a positive end. It's what we call a permanent dipole. Two poles, positive, negative. Those are the two poles, okay? So this would be a polar molecule made of polar bonds. I want to split those two. And there's a very good reason why. Because not all polar bonds lead to polar molecules. Here's a good example. I want to do this. I'm going to draw this molecule here. How do I know carbon has 4 hydrogens and not 6? And how much does it need to be perfect? And how many partners does it need to be perfect? 4, right? Because hydrogen has 1, right? So hydrogen shares that first one with carbon. Then it needs 3 more of those situations, and then it fills it up. So all carbons will have 4 bonds to it because it has 4 valence electrons. So what is this molecule? This is methane, right? Of fart fame, for those of you who love a good fart joke, right? This is the gas that you can light on fire. Wouldn't suggest you try that experimentally, just it happens. It's this is what we refer to as a hydrocarbon. Or we'll talk more about that actually when we get to the macromolecules chapter. But let's take a look first of all at these 2 components, like we did here, right? Let's break the bond down and let's take a look at the molecule. So the bond that we have inside methane is the carbon-hydrogen bond, yes? Is that polar? Okay, let's break it down. Is the electronegativity of carbon greater to, equal, or less than the electronegativity of hydrogen? It's greater, right? So is this a polar bond? Yeah, right? This is a polar covalent bond. Now, is it as strongly polar as an oxygen-hydrogen pairing? No, because oxygen is even greater electronegativity, right? But it is polar. Now, here's the question. This is a polar bond. But is this a polar molecule? It's not, but not because of the electronegativity part, right? But because of the electron cloud is going to get sucked in toward the carbon, yes? But it's symmetrical. So you have a symmetrical distribution of the cloud. That is to say that you can't turn this molecule around and say, oh, there's the negative side, or there's the positive side, because it's evenly distributed. The cloud, even though it's piling up on carbon, is symmetrically distributed. It's not showing a positive versus a negative face, right? Think of electronegativity and the distribution of the cloud creating a dipole. Think of it as sort of like the lopsided washing machine effect, right? In a dipole or in a polar molecule, you have a separation of the cloud or a distribution of the cloud that creates the lopsidedness of it, right? The lopsided washing machine effect. That means all the clothes go to one side of the drum and it creates a closed rich area versus a closed poor area. Just like the same thing with this electronegativity, if it has a polar situation, will create the lopsidedness. So all the electrons will be tilted to one side, and then of course the other side will be positive. So you get that lopsided washing machine effect. That creates a polar molecule. But if you have even distribution, like in this one here, it's more like the clothes are evenly distributed around the drum, right? So do you have a disparity? No, it's well balanced. So you don't have a pole. You don't have a place where all the clothes are and a place where all the clothes aren't. So you don't have that separation. Then that means the molecule is nonpolar. even though the bonds inside it are polar. That makes sense? Now, why did I take you through that? Because you have to draw a sharp distinction between what's happening between two atoms at a chemical bonding level versus what's happening between two molecules, which is above the chemical bonding level. What we did here, and oftentimes what the slides don't show you, is what we've done is we've taken a step from one level of organization, remember the hierarchy, atomic level, and we've taken a step up to the next level, the molecular level. The second I drew this, water, we stepped from the atomic level up to the molecular level, and you have a different set of relationships to define at that level. And the slides don't necessarily make that clear. That's the reason why I make this distinction, and there's a reason why I want you to make this distinction at this point. Okay, we'll talk about that in a second. Oftentimes I get a lot of blank looks in this section because for a lot of you, this is a head scratcher. Yes, this is kind of like where a lot of students are like, wow, okay, it's getting real now. The barbed wire now is wrapped around those bare knuckles instead of, right, feather soft. It's getting a little dicey now, right? This is kind of like where it doesn't make a whole lot of sense because wait a minute, you got polar, you got non-polar, blah, blah, blah. Remember, a couple of things I want you to always remember. Remember the bonding, this ionic, covalent, nonpolar, and polar as basically different stopping points in a spectrum of relationships between two atoms' electronegativity. Let's define that. In a polar covalent bond, the electronegativity of atom A is going to be greater than the electronegativity of atom B. It's going to be lopsided. Okay. In a nonpolar relationship, the electronegativity of atom A is going to be equal to the electronegativity of atom B. It's going to be the same. Now, in the ionic bond, the electronegativity of atom A is going to be a lot greater than the electronegativity of atom B. So what you really have fundamentally that's predictive is a spectrum of relationships between two atoms' electronegativity and the consequences of that. Think about it this way. And I'm going to get anthropomorphic because this is probably something that most of us actually understand. This is very much like a custody battle. And there's different types of custody battles, right? So if you've ever looked at custody law, no custody case is the same, right? Each one of them is a very unique kind of a byproduct of the two individuals involved, right? And it's very much tailored oftentimes to those two individuals, what actually turns into the ultimate agreement. And so what I want to do is I want to take a look at the spectrum of sort of this custody. So you have custody, two individuals, two atoms who are negotiating custody over the kids, so to speak, right? That would be the electrons. So let's go to the first one and the most extreme version of custody, and that would be the ionic bond. So what would that be like in sort of like human parlance, right? Well, that one would be like the one night stand, right? This is like, you know, I just met you, we just had a kid. I don't even really know how to spell your name. I'm not even sure what your name is because that whole night was a blur. Drunken stupor, perhaps. And so in this particular case, it's like, you know what, that's great. But one partner is usually vested and the other is not. So let's imagine that I'm going to go deadbeat dad on this one. It can be deadbeat mom, by the way, but I'm going to go deadbeat dad. Deadbeat dad is like, listen, that was like an hour of my life, not the rest of my life. And so pretend like I don't exist. I don't have kids. I never met you. I'm out. I'm going to do what I want. I'm going to pretend like this never happened. Don't ever call me because I don't know you. right? And then of course you have the mom who's like, you know what? I've like wanted to have kids like all my life, and now it's my chance. I can finally have a kid. So I know I'm gonna hang on to this. This is gonna be my kid. I'm so looking forward to this. I wanted this so much. And so no, this is mine, right? This is mine. So as a matter of fact, deadbeat dad, I'm totally with you. You know, you're kind of a creep. I can't stand you. If I wasn't so slamming drunk, I probably wouldn't have even gotten anywhere close to you. But you can keep walking. And honestly, if you disappear from the face of the planet, hopefully in a flurry of violence, then the world would be better for it. Now that's pretty real, isn't it? That's how it goes down. Some of you guys are like, that sounds familiar, actually. I think I just had this conversation with a few folks, right? So that would be like an ionic bond. That is a custody negotiation, by the way. I don't want it. It never happened. Don't ever think about me again, right? So in the case of an ionic bond, and sodium chloride in particular, who's the deadbeat dad? Who? Sodium, right? It's not my electron. I never had this electron. I don't even know who you are, chlorine. Get out of here. And of course, who's the mom? Chlorine. And how are they both happy? As sodium ion, which basically means this never happened, and chloride ion, which like, no, it did happen, and I'm so happy it did because this is just such a cute little baby, and I'm like a mom, right? I mean, that's like what I always wanted, right? Those sorts of things. So that's like an ionic bond. That's pretty extreme, yes? Okay, now let's go ahead and get into the covalent situation. Remember, this is a situation where you're sharing the custody. Now, generally speaking, this is kind of what we get in most courts, right? So you basically have a couple who married or whatever, or not. But there's some sort of relationship there at some point, and it dissolved for one reason or another under various circumstances. And of course, now they've got this kid, and they have to come up with some sort of a strategy to determine, okay, wait a minute, we can't just all walk away from this, right? We have responsibilities now. The relationship is gone, certainly, but now there's this thing, right? So how do we do this? Now, generally speaking, oftentimes what you'll see is a type of a polar covalent relationship. That is to say that generally speaking, there is a dominant parent, right? So the one that raises you for the most part, right? Often historically is the mom, but not always. It's becoming the dad more and more often in some cases. But the idea is there's clearly a dominant parent. And then of course you go to court to determine what the nature of the other parent is going to be, right? So in some cases, this can sort of vary from, you know, just stop by on holidays or whatever, birthdays and that sort of stuff, or it could be every weekend. It can be, you know, it can range, right? So it could be a lot, it could be very little. And there's an entire spectrum of contact for that non-dominant parent, but there's clearly a dominant parent, right? The everyday one, the one that's waking up in the middle of the night for the kid who's just got a bad dream, which if you're going through that, you probably have lots of bad dreams as you're going through all of that. Or when they're sick and they're hawking chunks everywhere, the dominant parent is the one cleaning it all up and that sort of stuff, right? So you can imagine that there's various spectrums of involvement here, right? So if you're the non-dominant parent, then depending on how close your affinities were for the kid, it will have a range of possibilities, okay? Now, a non-polar covalent is kind of like the relationship that's very rare, actually. You see this rarely, but you do see it from time to time, where there's perhaps a kind of an amicable parting between the two. They realize, listen, you know what? The relationship is over, but I think, you know, we're better as friends. We work together as a team better as friends than as spouses. And we're both very much aware of that. This is like a really amazing thing. We've got this kid that's really amazing, and we're both in it, you know. And so you act and work together as equal partners in the kid's upbringing. So this is kind of a situation where, you know, I mean, there's obviously going to be a house where the kid stays, but I mean, both parents are sharing the responsibilities you know, going to school, picking kids up from school, taking them to the doctor. I mean, they're switching off, they're acting like a team back and forth between each other. They're equally vested. They've got an equal attraction to the upbringing and the responsibilities for that kid. It's an equal custody share. That's what a non-polar covalent is. You have an equal electronegativity, so you're sharing custody of these electrons equally. Whereas the polar, there is a disparity. You're sharing, there is an interest there, but it's not an equal sharing. It's a lopsidedness. So one parent is shouldering most of the load while the other is not as dominant. And so that basically is that's the reason why I say that is because even though it kind of seems like analogous, it's actually not, because that's actually the way the atoms behave. They behave literally like a chemical version of the way people behave when they're in the middle of these custody agreements and custody negotiations. Now, for many of us, the whole idea of electronegativity and polar covalent bonds may not mean a whole lot to us. But for many of us, maybe the description of them as sort of being similar to custody, maybe that one makes a little more sense to us. Okay. Because many of us have gone through custody one way or the other. It's never a pleasant process. But by the way, if you're wondering, for each one of my little examples of each of those three, those are actually based on actual real people that I've known in my life. So this is, by the way, this is how you know you've crossed over to the dark side and you're total nerd. Is like when you start to see social phenomena, like as an analogy to like nerdy stuff, like science stuff, like nobody in their right mind should see like chemical bonding when they're looking at custody things. I mean, that's just unfortunate the way I think. I think in terms of analogies. Okay, so that's that. Hopefully that'll make that a little easier to kind of understand and sort of wrap your head around, because I know that does get a little tricky and a little slushy when we kind of move through the chemical bonding, especially when we toggle to the next slide. And this is what I mean by the slides don't really make this clear, because now all of a sudden we get to the slide called hydrogen bonds. The problem is these particular things are not bonds at all. And that's the problem. And that's the reason, by the way, I wanted to go through this with you, this whole difference between a polar bond is not the same as a polar molecule, right? Because I want you to make sure you're understanding and aware of shifting from the atomic level, right? Atoms that are either sharing or transferring electrons with each other based on their electronegativities in order to satisfy each other's octet rule, to the next level, which is the next step up, which is molecules now interacting with each other with a different set of rules. Okay, now are they related to these? Yes. But are they exactly these? The answer is no. Okay, and so sometimes that really confuses students, especially when you call one of them a hydrogen bond. Really, the next two slides are better understood, not as bonds, but as intermolecular forces of attraction. And if you think about it, that's exactly what they say they are. Attractions between two molecules, not bonding between two atoms. Okay. So from this level out, we're not looking at necessarily polarity of bonds per se. We're mostly looking at polarity of the molecule. Okay. So let's take a look at a hydrogen bond. What exactly is a hydrogen bond? So a hydrogen bond, and I'm going to define it. Where should I define it? There's a lot of blah, blah, blah on this slide. I'm going to define it down here. The hydrogen bond, oftentimes H bond, is defined as the electrostatic attraction between the positive hydrogen of one molecule and the negative oxygen, nitrogen, or fluorine of another. However, in biology, you saw our list of 12, right? Is there any fluorine on that list? Nope. So fluorine does not exist in your body. It does in chemistry. In chemistry, you use the oxygen, nitrogen, fluorine because you're always playing with all sorts of stuff in chemistry. But in biology, there's no fluorine. So mostly what we're talking about is the interaction between an oxygen or nitrogen and the hydrogen. So let's take a look at this. We already looked at this sort of dipole thing, right? This sort of idea where you have this sort of negative pileup due to electronegativity on one side of the molecule and the relative positive where those electrons kind of vacated, right? So what you have then is oftentimes, let's say I'm going to do an oxygen, you'll have a molecule where the electronegative oxygen will have a slightly negative-ish charge to it because of its electronegativity. And then a hydrogen from another molecule will be slightly positively charged. So this would be molecule A. I'm just going to be like molecule A, and this will be like molecule B. Okay. Now, when you see this, the positive negative will form a little attraction, and that is going to be your hydrogen bond. So the important thing to understand about hydrogen bonds, which is not true for covalent ionic bonds, is that these guys are weak. They're weak bonds and they're reversible. That's what transitory means. Is a covalent bond weak? What does it take to split two oxygen atoms apart from each other? A lot of energy, right? Think about it. When you're talking about covalent bonds, ionic bonds, these guys are together because they've made themselves perfect. Do you think they're motivated to fly apart from each other? No. So these guys do not want to go anywhere. So if you're going to be splitting these guys apart, it's going to take a lot of energy. So these are very strong bonds, not reversible, which is good, by the way. Because what that means is all that carbon, hydrogen, oxygen, nitrogen that you're made up of is not in danger of flying apart, which is helpful because then we'd basically just be dematerializing. And that would be difficult, right? To be functional throughout the day if you keep dematerializing all day long. So these are different, right? Because there's a different set of functions that you're trying to achieve with this. Now, each one of these individuals is weak. Now, let me explain to you what I mean by this, by explaining to you another separate set of scenarios that are exactly the same physics, Electrostatic attraction between positive and negative is nothing rare in the universe. We see it all the time, everywhere. And this is just another example of this positive negative attraction. Here's a good example of what I want to illustrate. Take a balloon, rub it on your head, and let it go. What's going to happen? Yeah, it'll stick there, right? Is the balloon going to fall off? How is it staying there? Exactly. So staying there by the exact same physics that holds these two molecules together with a hydrogen bond, this electrostatic attraction. So what's happening when you're rubbing your head with the balloon is you're rubbing electrons off of your hair. It's accumulating on the balloon. What you're getting is charge disparity. So one of you is looking more negative and the other is looking more positive. And so the buildup of electrons on the balloon is attracted electrostatically to what looks like a buildup of positive charge on your hair. And so it stays there. But is it actually permanently a part of your head? No. Is it easy to take off? Why? It's weak. So the fact that that those electrostatic attractions are a weak interaction allows you to be able to pull that balloon off of your head, no harm, no foul. Now, what would happen if instead this balloon was connected to you by covalent bonds, real bonds, the strong ones that we just talked about on the previous slide? What would that look like? Would you be able to pull a balloon off your head? No, the balloon would actually be like part of your head. It would be like a little appendage sticking out of your head. And if you wanted to cut it off, you'd literally have to cut it off. That would do damage to you right? So that would be like a permanent structure. You'd have a balloon stuck to your head for the rest of your life. That's what those covalent bonds do. That's the difference between a covalent bond, sticking something together with a covalent bond, versus one of these. This is weak, and it's intended to be reversible. That's the way it's supposed to work. So what does that mean? The other thing it also means is that there's this sort of sense of cumulative. So a single bond is very weak. But many are strong. That's an R-A-R-E. I just kind of got too close to the edge. So what does that mean? Well, let's take a look at an example. How about a gecko? Gotta love geckos, right? Anybody ever have a gecko? Have you ever seen a gecko? Like in a pet store or something like that? See him walking up the side of the terrarium? Have you ever wondered, because the gecko's not small. I mean, it's a full-size creature. I mean, it's about, yay big, right? So, I mean, it's got some mass to it. It's not like microscopic. Have you ever wondered how it is that a gecko manages to walk up the terrarium? If you've ever looked at it, it's actually quite fascinating. Look at a gecko, just watch him. Watch him kind of walk up the side of the glass terrarium. The gecko has some mass to it, right? So the question oftentimes is, how does a gecko stay on the glass? Well, let me show you what his feet look like. His feet don't look like an octopus. So there's not like little suction cups on there, where you can stick it on the glass and kind of like walk up the side. That's not what it looks like. What does a gecko's foot look like? They got like little slotted flaps, right, of skin on their feet. That's it. Matter of fact, when you look at it, it's like, how can you possibly hang on to the side of the glass with that structure of a foot? Well, actually, as it turns out, what's on those little slotted flaps on his feet is a bunch of hydrogen bonds. So a single hydrogen bond, like the balloon, falls off easily. Is that going to hold your weight? If you put a gecko on top of that balloon, is it going to hold the weight of the gecko? No. But there are so many hydrogen bonds on the foot of a gecko that it forms a hydrogen bond with the glass, and it allows the gecko to be able to hang on to the glass. Why? Because there's a lot of hydrogen bonds. Remember, in numbers, hydrogen bonds can be quite stable. However, are they still reversible? Sure, of course, because the gecko has to pull his foot off the glass too, doesn't he? Have you ever seen, actually, I've had a couple of my other sections, some students had geckos, and they were kind of explaining the way the gecko kind of peels his foot off the glass. Have you ever seen a gecko actually lift his foot off the glass? It's not just like pulling it straight off, right? Because you would have to be fighting the force of all of those billions of hydrogen bonds. That's a lot of strength that you're pulling against. You're not going to be able to pull that off, right? But what does the gecko do instead? Peels it off, one little flap at a time. So I can't pull all these hydrogen bonds off because that's too much strength, but I can pull this little strip of hydrogen bonds off because there's not as many. And then I can pull the next strip and the next strip and the next strip, so I can kind of peel my foot off and then lay it back down. So that's a really good point. Because of their weakness, it makes them reversible. But when you want strength, you just make a lot of them. What does that give you? It gives you a lot of flexibility. So if you're putting together a molecule which is interacting with other molecules through hydrogen bonds, then you've got this whole spectrum of interactions. Together with lots of them, they can be quite strong. Or you can make it quite weak by not having as many. A good way to think of, I'll save that idea until we get to water. Okay. So that explains then kind of this idea of polar bonds, right? Because if you take a look at polar bonds, you have to have a positive end and a negative end, right? So these guys are polar molecules. That's great. That's great. So that tells us how polar molecules can stick to each other, right? Doesn't really tell us anything about nonpolar, does it? So there's always this question, how do nonpolar molecules stick to each other. I mean, think about it. You pour oil. Does the oil molecule just fly apart? No, it pours out in a column, right? That means all those oil molecules are sticking to each other. Well, how do they stick to each other? Because if our entire concept of the way molecules stick to each other is through these electrostatic interactions, nonpolar molecules don't have those, do they? They don't have a positive and a negative pole. So how do they stick together? Well, they stick together with a different type of intermolecular force of attraction called van der Waals attractions. This is also a weak one. It's actually weaker than a hydrogen bond, but it's just enough. And so basically what this is a force that's caused, and I'm going to write a bunch of big words and I'm going to have to break them all down. Caused by the ephemeral flickering clusters of charge that form a temporary dipole on nonpolar molecules. Wow. Okay, there's a lot of words in there. Most of them I don't know. Right? So what is ephemeral? It's like an SAT word. So ephemeral is basically a fancy word for basically means that it only lasts for a brief moment. It's here, gone, right? Don't blink because you're not going to see it, right? It's just, it shows up, boom, and then it's gone. So what you have actually in these nonpolar molecules, and this is what I want to explain here. So here's your two nonpolar molecules. Remember, they're not dipoles, right? So they don't have a positive and negative pole to them. So the question is, how do they kind of do this? Well, think about it this way. Remember, the electrons in the clouds are basically whizzing around, yes? We're good with that one. And they kind of whizzing around roughly randomly, but within their orbitals, yes? Well, every now and then, just by happenstance, right? Just by dumb luck, chance, probability, all the electrons, like a lopsided washing machine, will just, for a moment in time, all converge, happen to be coming all at the same place at the same time, right? So we're all like right here together. Okay. When that happens, where we are, we create like a little patch of negativity. Now, where we're not is going to look slightly positive. But guess what? This gives us our little cluster of charge. That's what that is, right? But guess what? It doesn't last very long, does it? Because we're constantly in motion. So even though right now, in this point in time, we may be right here next to each other and have a little negative patch right here, within like a fraction of a second, we're going to be off somewhere else. So we're going to disband and we're going to go somewhere else. So that little negative patch that basically comes together, it'll disband, it'll come together somewhere else, and it'll disband, it'll come together somewhere else. And so just by random chance, every now and then, these electrons will come together in such a way that it'll create kind of a negative-ish looking patch. And of course, there'll be a positive-ish looking patch on the other side. And because they keep disbanding, reforming, that gives you that flickering idea. So you don't just have clusters of charge, but you have these flickering clusters of charge that are kind of like, they're there and then they're gone. And they're there and then they're gone. And they're there and then they're gone because they're constantly moving around. Okay. Now, ephemeral basically means that when we form a patch, we don't just sit there. We like immediately, we're gone. So we don't last very long. Okay. Now, what does this do? What this does is this creates what we refer to as a temporary dipole. For that brief fraction of time, this molecule looks like it has a positive and negative pole. It doesn't last very long, but it does at this particular junction in time. Like if we freeze frame it, it looks like it has a positive and negative pole. but it's temporary, right? Because we all basically disband and then we move off somewhere else. That's why we call it a temporary dipole. Well, guess what? The other nonpolar molecules doing the same thing. So maybe its little positive patch will see my little negative patch, and then it'll kind of form just a little bit of an attraction between us, just enough. But guess what? It's not like a hydrogen bond. It's not a stable association where we're sort of held together, because as soon as we kind of feel a tug on each other, it's gone and we let go. And then we'll feel another one and it's gone and let's go. And then we feel another one and it's gone and let's go. So it's constantly going back and forth. So it's like, oh, I feel it. Yeah, no, it's gone. I feel it. Oh, it's gone. Oh, no, it's over here. Oh, that's gone. Right. So you're kind of constantly sort of doing this sort of oscillation, this sort of vibrating back and forth as you kind of are drawn to each other when you're in your temporary dipole state. And then you just kind of like float away from each other when it gets disbanded, and then you get sucked into each other. So in reality, if I were a nonpolar molecule, I wouldn't be necessarily just like zeroed in on Connor the way I would be if we were like two polar molecules, right? It would be more like, okay, I kind of feel the temporary dipole and then I let go. And then I kind of feel the temporary dipole and then I let go. And then maybe I kind of start feeling a little tension between the two of you guys, but then I let go. But then maybe I'll start coming in here and feeling some more. And so I'll be kind of like, okay, then I'll let go. So then I feel it again and then I let go. And then I kind of just sort of milling about as I kind of feel that tug from that temporary dipole state from different individuals. So if all three of you happen to be the same thing, then I'll kind of feel a little bit of a tug between three of you. But it doesn't matter if I go to one or the other, because that's not the point. The point is that we all kind of stay together. We all kind of like overall as a group, we're kind of like still kind of mixing through the crowd, so to speak, and we're all stuck together. And that's basically how this works. That's just enough to keep all these nonpolar molecules together. That's the reason why oil pours out as a column and doesn't fly apart. So before we get into water, we got to say a couple things about chemical reactions. Why? Because this is the process by which atoms decide how to share electrons or transfer electrons, right? So I should probably put share / transfer. So remember, in a chemical reaction, you're always going to be dealing with an atom. You're going to be dealing with their octet rule, and you're going to be dealing with their relationships with each other. In a chemical reaction, you have a couple of major parts that always recur. So first of all, on the left-hand side of a chemical reaction, you have what's called the reactant. So these are the molecules that you start with. Then you'll have an arrow which denotes the reaction progress, and then you'll generate some sort of products. Now, in a chemical reaction, and you have lots of them in your body, typically there is one chemical principle that we always want to make sure we keep in mind, and that's called the law of conservation of mass. Anybody know what that is? It's a chemistry law. It's one of the ones you learn about in Chem 1. But basically this law says that in a reaction, mass is neither created nor destroyed. So what does that mean? So what that means is the stuff that you start with in the reactants has got to equal the stuff that you end with in the products. Let's take a look at this. So you have no change in mass. What does that mean? That means that if I have X number of carbons on one side, I have to have how many on the other side? The same amount. Okay, let's take a look at this reaction that we have here and see. How many carbons do I have here in the reactants? So you have 6 molecules of CO2, right? Okay. Well, this is 1 molecule of CO2. You have 6 of them. That's what that means. So this number is the number of molecules of CO2 you have. Okay. How many do you have in your products? So you have 6 carbons, as I'm looking at. Right, 6 carbons. Okay, now let's go ahead and do the oxygens now. How many oxygens do I have? Yeah, so you have 2 per CO2, right? You have 6 of those, that's 12. You have 6 more over here because you have 6 oxygens. That gives you what? Okay, now how many do you have over here on the product side? So you have 12 here, right? Plus 6 here in this one. So you have 18. How about your hydrogens? So you have 2 per oxygen, right? So you have 6 of those. And how many do you have over here? Yeah, they're all in the yep. So did you lose anything? Did you gain? So what happened then? If you neither gained nor destroyed atoms, what happened? Exactly. So all a chemical reaction is taking existing bonds between 2 atoms, breaking them. That's a big ask, right? That's an energetic ask. That's a tough thing to do because they do not want to they're happy now, right? They do not want to break. And then you're basically reassigning them to other atoms. So you're basically breaking existing bonds and you're reforming new ones. Why are you reforming new ones? Because the new arrangements may give you more biological function. Right? For instance, this one right here, that's our glucose, right? That's an energetic molecule. So that's a good thing. That's what we want. But we have to break bonds to get there. Okay. And that's basically what a chemical reaction is. You're breaking existing bonds so that you can rearrange them into new bonds that give you biological function in this particular case. Okay, let's take a look at a chemical reaction. Now, what sorts of things will affect the rate or the speed at which a chemical reaction occurs? Well, first of all is temperature, right? So if you increase temperature, you'll increase your reaction rate. That's an easy one. We do that all the time, by the way, right? If we have a particular reaction, some of you guys may have played this little game, right? So you kind of heat things up. Every time you make Jello, by the way, you're playing this little game, right? Because you have in this case, the rate of dissolution, the dissolving of the sugar or the fluid or the Jello happens very quickly or slowly if it's in cold water. It's very slow in cold water. So what do you do? What's the first thing you do in Jello? You don't add it to cold water, do you? What do? You boil water, right? And then you add it to that. Why? Because you want to speed up the reaction of dissolving the Jello in that. And then what do you chase it with? You chase it with cold water, right? Do you have to? No. It'll harden up when it cools up. The reason why you pour water, cold water in it afterwards is so that you can actually enjoy the Jello sometime before you die. Right? That's a little extreme, but that's the reason why, because let's face it, normally the consumers of Jello tend to be under the age of 18. And your patience under the age of 18 is also very challenged, right? So chances are that you've got a whole lot of tiny, hungry little mouths and anticipation. They're high on anticipation, low on patience. And so they're not willing to wait, forever for hot Jello to solidify. So what do? You chase it with cold water to sort of speed up the setting process. That's the only reason why you're chasing it with cold water, by the way. There's nothing magical there. But that's a good example of the rate versus temperature. You can also screw this up in good or bad ways by dumping more reactants or products. So if I dump a reactant to it, what it's going to do is it's going to basically force the production of more product. If I dump a bunch of products into it, it's going to force it in the reverse reaction. Okay. Now that gets us to this idea here that we'll touch on, but I want to talk about catalysts because catalysts are big. So a catalyst is something that has 2 parts to it. By definition, it's this chemistry definition, and also here's the biology. Anything that has these 2 properties to them is defined as a catalyst. First of all, they have to be able to speed up a reaction. Got to. If you're not doing anything to the reaction, you're not a catalyst, right? That's the whole point of being a catalyst, is to speed up that reaction. The other one that's also important is that you are also not consumed by the reaction. So the reaction doesn't touch you. All you do is facilitate it. If you are altered, or consumed by the reaction, you are no longer a catalyst. You've become a reactant. Okay, so you are a participant in the reaction, not a facilitator of the reaction. Okay, and that's important. Now let's get back to this idea of reversibility. Now, this is a big thing here, right? I mean, in chemistry, they talk about this, but they don't usually talk about this until like Chem 2, when they talk about the equilibrium, chemical equilibrium. And that's really important. But in biology, we're only interested in reversible reactions. And in chemistry, for the most part, you're interested in reactions that go to completion, right? Because a lot of times you'll do funny little things like calculate your percent yield, right? And the idea is that you kind of calculate it on paper using stoichiometry, and you kind of predict like, well, I should be able to get X number of grams of product out of this reaction. And then you do the chemical reaction. And the idea is what you actually get, hopefully, matches what you calculated to get, right? Kind of the difference between the two is your percent yield. Okay. And in order to do that, however, you want your reaction to go to completion, right? So you want the reaction to completely convert over to your product, because otherwise you're losing product and you're going to lose your percent yield. And so I say that to basically say, not to scare you from chemistry, but I say that to basically say in chemistry, we're oftentimes focused very much so on completion of reaction. In biology, it's completely the opposite. We're not interested in complete reactions. We're interested in reversible reactions. So for instance, we see this, A plus B goes to C plus D as equal in merit to the reverse reaction. C plus D goes to A plus B. Now, why do we want this to be reversible? The reason is because circumstance A may require us to have C and D in order to be able to meet the circumstances. However, circumstance B may require us to have A and B. So it really depends then on what our circumstances are as to which direction this thing goes. So rather than looking at, I always like to think of it as like a fighter, right? Think of and what are the circumstances? The circumstances are basically our environment. And we live in Denver. Most of you probably lived in Denver long enough to know our basic mantra, right? What is it? If you don't like the weather in Denver, yeah, wait 5 minutes. So basically what that means is environmentally, we have a lot of things getting thrown at us like all the time. Our environment's constantly changing. Nothing is static. So we have to be dynamic along with it, right? So think of the environment as being like a prize fighter that you're up against. And I mean, you're getting jabs, you're getting hooks, you're getting all sorts of stuff coming at you. Well, if you have a reaction that is specifically matches the particular punch that's coming at you, then depending on what's coming at you, you have to be able to either break right or break left. Think of it this way, right? If I have, let's imagine that I'm right in the middle, right? And so if I move to if I kind of, duck left, that's going to be like A and B. If I duck right, that's going to be C and D. Well, I have to, as a fighter, be able to do both, dodge to the left and to the right, right? I have to be able to go back and forth. Why? Because if I see the right hook coming and I only go forward to C and D, guess what I'm doing? I'm leaning into the punch. Bad idea. That right hook is going to plaster you, right? But what you have to do if that right hook is coming is do what? Dodge left, right? Because even if it gets you, you're going in the same direction as a punch. So it's only going to be a glancing blow. You're absorbing the energy. So you guess what? You get to stay on your feet, don't you? So you have to, depending on what's happening, if you're seeing a left hook coming at you or a right hook coming at you, you have to be able to make a decision which direction to dodge so that you don't just lean into the punch, right? That's exactly what's happening with chemical reactions. The environment is throwing right hooks and left hooks at you. And your chemical reactions, you have to be able to arrange these in such a way that will allow you to either be able to duck left or duck right so that you can adapt to what the environment is throwing at you. That's the reason why we're always interested in biology in reversible reactions, because your circumstances are never the same. They're not static. They're always dynamic. They're always changing. So whatever you do, you oftentimes have to undo, right? And then you have to redo it and then undo it. So how many times during a fight am I going to have to go left versus right? As long as the fight is on, right? So it's like, okay, I'm doing it, undoing it, doing it, undoing it, doing it, undoing it, doing it, undoing it, doing it, undoing it. And how long does this fight last? 80 plus years, however long we're alive. You're just doing it, undoing it. So you have to have not just reversibility, but you have to have stable reversibility. That's you have the ability to go back and forth and 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 on and off and on and off and undo, right? Undo, do, all of it, back and forth, as many times as you have to in order to dynamically adapt to your environment in real time. You only can do that if your reactions are reversible. Does that make sense? The other analogy I like is the light switch. Perfect example. Is a light switch a reversible mechanism? Sure, right? On, off, on, off. How many times do you think that light switch has been turned on, off? See, this building has been here since about 2010. Thousands, depending on how heavily used the room is. How about, because this is a lesser used room. How about our labs? You have 13, 11 sections per week cycling through that room. Times 16 years. How many times do you think those light switches have been turned on and off in the bio lab? Is millions too many? When we go in there on Wednesday, will we be able to turn the light switch on? Will we be able to turn it off? We'll be able to do that all semester long. Will we be able to do it for as long as we need it? So our value in that particular system is its reversibility. Lights on because we need it. Lights off because we don't. And we're going to need it again, and then we're not. And we're going to need it again, and we're not. And we're going to need it again. Why? Because our circumstances are constantly changing. Okay. That's why our reactions are reversible. And that idea of the light switch is a very important analogy to learn, especially if you're going into AMP. Okay. Okay. So we're going to start talking about molecules, but we're going to talk about the best molecule of all, right? Water. So water, we've already seen the structure of, right? So you have an oxygen with 2 hydrogens associated with it. And water is actually governed by the hydrogen bonds. Matter of fact, a lot of the properties of water we're going to be talking about are driven by the hydrogen bonds themselves. And water is so important because the way water is, and water is a very simple molecule, right? 1 oxygen, 2 hydrogens, dipole. But its structure through the hydrogen bonds is what allows us to have an enormous amount of benefit. And there's a reason why when we're looking on other planets for other life, what are we looking for? Not just any water, we're looking for liquid water, particulate, right? We're happy if we see ice, we're okay with that one, but liquid water, woo, that's the one we want. Why? Because basically this is essentially our elixir of life. Don't know how to spell that. Take a look at your blood plasma, it's 92% water. Most of your cells, water. Okay, so you are mostly made out of water. Most living organisms are made out of water. Okay, water is the primary commodity on this planet, more so than anything else. So it's a big deal. And so we want to take a look at the structure of water. We've already looked at its polarity, right? We already know that water itself has a negative oxygen side, has a positive hydrogen side. So that kind of creates this sort of polar atmosphere of water. Go ahead. Well, a meniscus. Yes, we'll talk about that. The meniscus effect. Actually, it's the opposite way. So you went this way. So it's actually a concave view. But we'll see why exactly. But that is part of the properties of water that causes that. We'll take a look at that. But basically, this gives oxygen a partial negative. This is a typo, by the way. Make sure you change it in your notes. So it's actually partial negative on oxygen, partial positive on hydrogen. It's was backwards in the notes themselves. So in the slides. So we already have that. Right? It's a very simple molecule. And the other thing I want to do before we start moving into the properties of water is explain a little bit as kind of an extension of the structure of water, right? So this one here, we kind of already see, this is your Bohr model of water. And we kind of build this one out, right? So here's your two lone pairs there. And then of course, these are the other two that are interacting with hydrogen, right? So that's basically what's happening here. So you have 1, 2, 3, 4, 5, 6. You have one hydrogen there, another hydrogen there. So that's going to form those two bonds with your two lone pairs there. Now, as it turns out, when you have these four slots, so these like 2, 4, 6, 8, right? This 8 in those electron shells. So these kind of these dual pieces. So this is like, this represents an orbital. There's an orbital. There's an orbital, right? That's that ZP, XP, YP, and then that's the S orbital, right? So those are those individual orbitals. So these individual orbitals, when they come together with the hydrogens, when they kind of sort of sort all their electron cloud out, actually creates a specific shape in these molecules called the tetrahedron, where basically you have in the center the central atom, and what it forms geometrically is this kind of like pyramid with like a little stick on top. So a lot of times students will ask me, well, how come you always draw water as a bent molecule? Why not straight? And the reason is because it is bent. And here's what it looks like. So of these four, these are those four orbitals, right? 3 P's and 1 S. So 2 of these are going to be those individual lone pairs, right? So they don't need anybody because they're there already. And then the other ones are going to be associated with the sharing of hydrogen. So you have these two guys here, which are shared with hydrogen. I'm going to put these guys there. So there's my 2 shared with hydrogen. So as you take a look at it then, these don't really create a lot of space requirements. They kind of get sucked and held down in close to the oxygen, but these do. And that's the reason why what you have left over is this sort of bent shape. So you can see here, this is where the 2 lone pairs are. And then this is the bent shape left over. That's the reason why you always draw water molecules as a bent structure, bent molecule. Okay, so what I'm going to do next time is I'm going to start with the unpacking of the properties of water. Okay, so going from our structure of water to building out the properties of water.